All right, guys, this will be our second lecture. This will be section 1.6 on first order linear differential equations. As usual, we'll start with our requisite skills, and not a whole lot you'll need past section 1.4. We still will need some algebraic manipulation, the ability to move things around an equation, as well as the ability to integrate. Okay, some integration techniques, by parts, substitution, whatever it is that the problem calls for. Things from Calculus 2. Okay, so this is another section based on just a singular technique that we're going to use to solve a specific type of differential equation. So a few questions though. What do we mean by first order linear differential equations? So a first order linear differential equation is any differential equation that can be written in the following form, right? So what I have is I've got some function of x. I don't actually know what that is. It could be anything, right? Just maybe a bunch of x's. Times y prime plus some function of x times y is equal to, well, some other function of x, right? So the important things here is that what I actually have is that I have y prime, y, and then nothing here, and maybe I've got some x's attached on the front, all right? But notice this is linear in y, and it's linear in y prime. That's where the linear differential equation comes from. It doesn't mean the whole thing is linear. It means that it's linear in these particular variables. And it's first order because it only involves that first derivative of y. Now this is a bit it's a bit unsimplified, right? If I have something in this form, honestly, I could just divide everything by a of x, by whatever this function is. I can divide everything, and that'll give me a new function in x. Whatever the function b of x divided by the function a of x is, will just give me another function. So really, and this is the version we're going to work from, really, first order linear differential equations are those that can be written in the form y prime plus, if I take the quotient of those two functions, I'm just going to rename that some function p of x, okay, times y is equal to, again, dividing everything, so r of x divided by a of x. I'm going to call that q of x, right? So really, it looks like this, and we call this one monic, right? So monic just means that first coefficient is 1, right? So we're going to operate from this particular version of a first order linear differential equation. Now, what are we going to do with this? Well, it turns out that the structure of this is simple enough that we can come up with a method for solving all first order differential equations, okay? So let me work through that. Now I'm going to work through this without a specific example first, and then I'll go back and I'll do an actual specific example, and I'll point out a couple places where students have some pitfalls. Okay. So what I have currently is I've got y prime plus p of x, don't know what that is, times y is equal to q of x. Okay. So how can I solve this? Well, I'm going to make an assumption first. Okay, I'm going to make an assumption. I want another function which I'm going to call an integrating factor. Okay, so I want what's called an integrating factor. Okay, this is going to be I of x. And I'm going to define I of x to be e, and the exponent here will be the integral of p of x dx. Okay. Now I want to just spend about 20 seconds talking about this. Here's what I'm really looking for with I of x. I'm looking for some function to where the derivative with respect to x of that function I want to be p of x times I of x, right? So I want the derivative of whatever this is to be p of x times I of x. Okay? And you'll see that this does fit that criteria. If I take a derivative of this function here, it's e to a function, so the derivative of it is itself, times a chain rule where you take the derivative of the exponent, derivative of the exponent is p of x. Okay? But I want you to notice something. This actually works. When I integrate this, I'll get an arbitrary constant, but this will actually work no matter what that constant is. Okay? Because when I integrate p of x and I get some function plus a constant, when I take the derivative of that, when I take the chain rule, the derivative of that constant will be 0. So when I actually figure out what this is, when I really work a problem, I'm not going to care what that arbitrary constant is because, and this is an important distinction here, I'm not looking for a specific integrating factor for this problem. I'll take any integrating factor that satisfies this condition. And any function of this form will satisfy that condition. And so I get to choose what the constant is. And I'm going to make a very judicious choice, and I'm going to pick 0 every time, right? Okay, so that's going to give me a nice, interesting function. I'll explain why we wanted this in a second, right? So right now, I want that function, that's called my integrating factor, that's I of x. Okay, now what am I going to do with I of x? Well, the first thing I'm going to do is I'm going to take I of x, I'm going to multiply it through this equation. Okay, so that's going to give me I of x times y prime, okay, plus, so I multiply this thing times I of x, so I'll get p of x times I of x times y, and that's equal to I of x times q of x. All I did was just distribute that I of x to everything in this equation. Okay. All right. And now for the critical part of this particular work, why did I want this? Well, I want you to notice something here. I'm going to relabel the parts on this side. Okay? If, hypothetically speaking, let's say I call this function f, right? Isn't this part f prime? That's what I wanted, right? I of x was constructed in this way so that the derivative of I of x is p of x times I of x, right? Yeah? So over here, we note that because of this construction, the derivative of I of x is p of x times I of x. So this is, if this is f, that's f prime. Okay? And similarly, if I label this g, then that's g prime. Right? Y prime. And now let's look at what we have. What I have is f times g prime plus f prime times g. Well, where have we seen that before? Well, that's the result of a product rule, right? I know that f times g prime plus f prime times g, this is just the derivative of f times g, right? That's what this is. This is the result of a product rule. And so what I'm going to do to continue the work on this problem is that I'm going to take the left-hand side, which is the result of a product rule, and I'm going to rewrite it as the derivative of the product. Okay? So let's do that now. Okay? So the left-hand side, we're going to rewrite as the derivative, okay, so d dx, the derivative of f, this was f, times g. Okay? So this, the derivative of f times g, that's equivalent to f times g prime plus f prime times g. So it's equivalent to that expression. Okay? And this is just equal to the right-hand side of my equation. Now this looks a lot nicer. Okay, this looks a lot nicer. Most notably, you'll notice that I no longer have a y and a y prime. I just have that singular y term when I work through this. Where do we go from here? Well, what we can do is that now I can integrate both sides of my equation. Okay, and I'll go ahead and integrate them with respect to x, since I have an x derivative here. Okay, so let's do the integral with respect to x on the left, and the integral with respect to x on the right. Okay, okay, on the right-hand side, we'll look at the right-hand side. On the right-hand side, I don't know what this is, because again, we're working somewhat abstractly here. I don't know what I of x and q of x are, but if you told me, I could integrate them, probably. Right? Okay, so I've got I of x times q of x dx. Okay, so whatever that is, we'll figure that out when we're actually working a problem. On the left-hand side, we've got an interesting construction here. I've got the integral of the derivative of a function. Okay. Is the integral of the derivative of a function equivalent to the original function? But no, actually, right? That's one of those weird things where the derivative of the integral of f is f. So for instance, this is true. The derivative of the integral of f of x dx is equal to f of x. That's true. If you think about it, when you integrate f of x, you're going to get some function plus a constant. And then when you take a derivative, the derivative of the constant will be 0. Okay? However, the other direction, the integral of the derivative of a function is actually a little bit less specific. It's actually the function plus a constant. Okay? So the integral of the derivative function is not exactly equivalent. So while I would like to just cancel these things out, the integral and the derivative, I can't really. Okay? What I really get is I'm going to get I of x times y. I'm going to get the function. And then I'm going to get plus c. But again, so I'm going to get a plus c here. But because of the very nice aspect of differential equations, because I'm taking the integral of both sides, I'm going to get a constant over here anyway. Okay, so I'm going to drop off the c that would go here and just lump it in on the right-hand side when I finally integrate that part. Okay, well, this is fantastic. Okay, this is fantastic because I already know how to finish this off if I'm solving for y. I'm going to go ahead and divide both sides by I of x. And so this gives me y is equal to 1 over I of x times the integral of I of x times q of x dx. Okay, fantastic. And so this gives me a general solution for any linear first-order differential equation. Okay, now I'm going to go ahead and work an example. I'm going to work one that it's got a couple little pitfalls in it, just because I want to sort of point that out so you guys can maybe see where you might go wrong. And we'll call it there. Honestly, there's not a lot of different ways for these problems to appear. They all use the same steps. So I'm only going to do the one example here. I am going to do, just like I did for section 1.4, I am going to do an application problem involving these. However, the application problems are in section 1.7, so that'll be in the next video, right? So this one, we just have the one, we'll just do the one example. It is a useful one, though. All right, let me see if I can write this down properly. We've got, here we go. We've got y prime minus xy equals x e to the x squared over 2. X e to the x squared over 2. And we probably need a domain restriction. No, we don't. Okay, fine. Okay, so let's talk about this problem. So what are we going to do? Okay, so first, if you remember, the first thing we did was we wanted to make sure that it was monic, that the lead coefficient was 1, because that's the version of the linear differential equation that we want to work with, right? So I need to make sure it's 1, but it's already 1. So good for us, right? There's already a 1 here. Fine. All right, the next thing I needed was my integrating factor, right? Okay, so my integrating factor is, so let's see, let me find I of x. So I of x is e to the integral of what's going to be the function attached here at y. Now this is very, very important. I want the end result of all this work to be a product rule on the left-hand side, right? The result of a product rule. Yeah, but product rules are addition, right? That means I'd like for this to be plus, okay? What that means is that I have to treat this as y prime plus negative x times y. If you don't move that negative sign, if you don't include that negative sign with this function, and hence in your integrating factor, your answer won't come out slightly wrong. It's going to come out very wrong, like really, really, really far away from a right answer. Okay, so be very, very good. It's a very common mistake. People make that all the time. Okay, so just be aware. Okay, now let's go ahead and finish this out. This makes my integrating factor e to the negative x squared over 2. Again, technically there's a plus c here in this exponent, but again, I'm not looking for a specific integrating factor. I'll take any integrating factor, so specifically, I'll take the one where c is equal to 0, and that's going to work just fine, okay? Because the derivative of this is itself times this function. All right, fantastic. Now, next step, I'd like to take this integrating factor and I'd like to multiply it through times my entire equation. So let's see what I get. On the left-hand side, I get e to the negative x squared over 2 times y prime plus negative x times e to the negative x squared over 2 times y. And on the right-hand side, let me just write it out. I'm going to get x, and I'm going to get e to the negative x squared over 2, and then times e to the positive x squared over 2. But the product of e to the negative x squared over 2 and e to the positive x squared over 2, when you multiply like bases, you add the exponents, right? And if I add these two together, I get 0. E to the 0 is 1. Okay? So this turned out very, very nicely. Okay, it turned out very nicely. Those actually, those multiply together to give me a 1. So this is nice. Okay, very, very nice. Okay, so what do we do from here? Well, again, our next step is to rewrite the left-hand side as a product rule, right? I mean, it is a product, is the result of a product rule, but I want to rewrite it as the derivative of a product. So, again, let's call this function f, then this function would be f prime, right? And if that function is g, then that function will be g prime, and that's what I want, right? F times g prime plus f prime times g. So let's rewrite this. We'll write it as the derivative with respect to x of f times g. So of e to the negative x squared over 2 times y. Okay? And that's equal to, again, right-hand side didn't change, it's equal to x. All right. Almost done then. From here, I want to integrate both sides. Okay, that'll get rid of this derivative. I want to integrate both sides with respect to x. Fine, 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 fine. Okay. The integral of the left-hand side, we get e to the negative x squared over 2 times y. Technically plus a constant, but I'm just going to lump that constant in on the right-hand side. And on the right-hand side, I get x squared over 2 plus c. Okay? All right, and the only thing I have left to do now to solve for y, is just to take this term and then move it to the right-hand side. We'll multiply it both sides by e to the x squared over 2, or equivalently, we'll divide both sides by e to the negative x squared over 2. They're the same. Okay? And the result of that is I get y is equal to e to the x squared over 2 times x squared over 2 plus c. All right, so here's another place where students tend to just miss a couple points, and I don't want you doing that, right? When you move this function, okay, you're going to multiply or divide it, it's got to be to the entire side. You will almost never have what I call a hanging c, right? In differential equations, you're almost never going to have a c all the way on the end, just added plus c. It's typically going to be multiplied by something, right? So here, again, this e to the x squared over 2 that we moved, it's multiplied times the entire right-hand side, okay? And that's it, right? It's a pretty straightforward process, yeah? Okay? All right, so these, not terrible at all. The good news for this particular method is the process never, ever, ever changes. But like the other one, I mean, I can make it more complicated, right? The question is, how easily does the right-hand side integrate? Yes? Here, it was very nice. That looked like what was going to be like a substitution integral, but due to some cancellation, it turned out really nice. Yes? Well, sometimes it may not turn out nice. Sometimes you might have to use integration by substitution or integration by parts, or really, you know, whatever integration technique you'll have to use. Okay? All right. So again, there will be application problems for this particular technique. Well, I'll do a mixing problem, but I'll put that in a separate lecture under section 1.7. Again, make sure you guys are looking over your homework, do that stuff ahead of time, and make sure that you write down and record all the questions that you have so you can ask them during our live sessions. Okay? All right.